I'm going to talk about PDKMaster and my standard cell generator and give you a little bit more later on. So my background, I've been working for almost 25 years at IMEC. In the last 7, 8 years, I was working on radiation-hardened SRAM compiler development. And we also had an I/O library, radiation-hardened, standard cells, SRAM, and I was actually the contact person, the first support to the customers of us. So in that respect, I got to know the full EDA flow from synthesis, place out, and all these things. But so as a hardware engineer as profession, or was as my profession, but I'm actually more a software developer by heart. So when I've been working, for example, on open source implementation of the Amiga OS. The Amiga was an old computer. I don't know, maybe some people don't know it. Likely, hopefully most of you do. And also I like Python. So I liked Stefan's talk yesterday, but when he said that he hates Python, then yeah, that caused some problems, but okay. So my personal motivation, so I think most of these things were already discussed yesterday during the panel. It's just to give you my background, why I'm doing the things I do, the way I do it. So for me, the main purpose of open source is not to get to open source, but is to build communities around implementing shared source code. So the main purpose is that you get a community built around your project. And that then generates source code, but it's the community that develops how you use it. Also, I was not really satisfied with what in my mind was a stagnation that you got from innovation from the EDA software companies. So when I talked with these sales guys of the EDA companies, I was felt very special, because with each feature request I came to them and said, oh, we never heard about that feature request. You know, you can understand that we cannot implement that. We don't have the bandwidth to implement that. So it's hampering innovation in that respect. What I also saw is that each PDK is different. So they have their own strategy of defining the design rules, LVS rules. Even if you have different fabs from the same foundry, they can have different strategies to define their DRC rules. And that makes it difficult to port it between different technologies, because you cannot derive actually directly the design data to generate layouts. And that was our main driver for starting PDKMaster. Also, I was not really happy with VSDL, System Verilog. To me, these languages felt too much designed by committee. Like I said, I'm more a programmer than a hardware engineer, and it felt that, yeah, for example, there was not a proper abstraction. If you write VSDL or Verilog or System Verilog, you actually have to know which hardware will be inferred to write good VSDL and Verilog. And in my mind, is that an indication of not a proper abstraction. Actually, at FOSDEM, I gave a few years ago a presentation about this. Personally, I'm an Amaranth user, but there are also options like Chisel, which are used by the Berkeley RISC-V guys, Spinal HDL. I've heard that from Norbert that there is Spinal HDL work going on here in IHP. So I think these are solving these problems. And then for analog design, the problem I had there is that it's mostly done design to spec. You give me a spec, an analog designer said, I cannot do anything if you don't give me a spec of the device. And then he makes the design according to that spec. And if you change the spec, then he has to start over. And in open source, what you want to do is you want to have a first design done and then continuously improve it. And I think you should find ways to do that. I understand you cannot do it for, I think, for RF applications that really squeeze out the last things. You probably cannot do it. You always have to optimize for your specific process. But for more generic analog blocks like a band gap and these kind of things, it should be possible, I think, to make portable, that are easily portable, that you don't have to redesign them each time. So my affiliation, so my work has been funded by NLET projects, and I'm also part of the GOIT project, that Parim just presented. Actually, 5 years ago, I quit working at IMEC and I founded my own Fibra service. I did some presentation and then I stumbled upon Rob Taylor and then he convinced me to co-found ChipFlow. So this is the website of ChipFlow, and it's based on this Amaranth Python-based hardware generation language and the backend in the cloud so that you can use software engineers to make chips and you don't need hardware engineers anymore. So about PDKMaster. So it's a Python-based framework, starting from the base to develop a good API. So when I quit IMEC, I said I want to do this right and not, but that takes time, of course, making a good API. And then using software engineering best practices for EDA. I have different modules, PDKMaster, a standard cell generator, an I/O generator, memory generator, and then some scalable analog blocks. I discussed this I/O and memory generator last year at FC conference, and I will have a talk on Free Silicon conference this year in 2 weeks' time. So I will focus here on the standard cell generator and PDKMaster. So currently I'm maintaining the open source PDKs actually, Sky 130, Global Founders 180, and IHP now. Unmaintained is FreeBDK 45, but also TSMC 350 and 180. What is interesting there is that my framework should also be usable with proprietary NDAs, proprietary PDKs. So I can do that, but my preference is of course an open source PDK, so that everybody can work on the results and on the IP blocks and all these things. So let's switch to some example. So let me first go to the browser again. So all my projects are open source, so they are on Chip4Makers part on GitLab. So I put everything on GitLab, and you can see that the code is, you have different projects for C4Makers, FlexCell, I/O, MEM, generator, the things I mentioned here, and then here you have PDKMaster. And if I then switch to Visual Studio Code, you can see that I've checked out all these code bases and I've added them here. And if you go to PDKMaster, so PDKMaster itself is the base. So it's a tool to manage PDKs for ASIC designs and designing circuits and layouts. And then the other tools are actually based on that. And if you look at the structure, you have the PDKMaster subdirectory here, which is the Python module that you can also install with PyPy. And it has 4 different sub-modules. The technology is actually the code where you can define your technology, your devices, your layers, and the design rules are actually derived from how you define your devices. I'll be given an example later on. Then design is based on that, how you make circuits and layouts with that. And then dispatch is just a helper function, and then I/O is actually helper functions to interface with other tools. So, and I have a K-layout helper function so that I can export setups for K-layout. So if we then go, I'm not going into detail in FlexCell itself, you can look at the code yourself, but I will discuss now the Sky 130 PDK I have support and IHP PDK. And so you actually have this FlexCell standard cell generator, and then you actually have to define 2 files for each technology node, which one is called the technology definition itself, and then one is just the setup for your standard cell generator. And this is then the file for Sky 130. So you have the technology for Sky 130. These are the pin layers for defining pins in your standard cells, the blockage layer, which is for place it out, where you don't want to place a route. Then you have the implant layers. You have the N plus implant layer, the P plus implant layer, and then the adjust layers for your VT, for your transistors. The N-well layer, and then a deep N-well, and then a high voltage layer, which is a thick oxide layer, actually. And then the recognition layers for your resistors. And then you define the active, which is called diff-top in SKY130. And you define your poly layer, your interconnect layers, your metal layers. And you can see you can use Python 4 generation. If you have layers which have the same design rules, you can, for M1 and M2, they have their own design rules, you can just reuse them. So you define your technology as Python code, the vias also for part of the interconnects. And then here below, you define your devices. You have resistors. And I wanted to go up. I think the more interesting thing is the transistors, of course. So you define a gate, and then you can define different transistors based on this gate with different implants. You have the same. A gate is basically a poly layer crossing an active area, so it's a cell-defined layer and these things. So that's for SKY130, and then for IHP, you do the same thing. I did that on the released open source technology description. I have done here the N-well region, the implants. One thing I had to do is, because I still assume now at the moment that your NMOS has an N plus implant layer. So I generate a virtual N implant layer because the IHP process just derives the N plus implant layer from the P plus and the N plus blockage layer. But you can just remove this layer and then it just is okay. Huh? But I will work on PDKMaster later on to actually that it's not needed anymore. So I do the derivation myself. And then, yeah, so you also have a thick gate oxide and these things. And then you just have to set up your standard cell generator. And it mainly is the setup for, it's just these 3 lines. You have to say which NMOS and which PMOS you want to use and which implant you want to use. You don't even have to, in all cases, give this because it can be derived from the NMOS and PMOS. This is still based on the lambda-based rules, but actually, I implemented that you don't need lambda-based rules and that you can define your, but that's, I wanted to finish that for today, but I didn't finish it, so that you can just define yourself the grout and VDD, metal line width, and these things, so that where the N-well is placed, that you can just have different parameters for this. It should allow more scaling later on. But again, open source, first implementation, and then improve it. Huh? So, and then you have this for SKY130, and then you have the same thing for ISP, where I then actually did 2 ones, one for the 1.2 volt standard cells and 3.3 volt cells. So I can generate them, but I can only generate GGS at the moment because I don't have a MOS model yet. So, and even PSP model may be difficult because I'm using a tool from Lib6 for the characterization, and it makes a simplification of the models, and it's not, we have to see if it can handle the PSP model. So if I then go to the demo, so to the dangerous part of my talk, do it clean. So if you do it, he has removed the Open PDK directory. If you then do a minus, so that's, do it is a Python alternative of make, actually. So I'm using do it because that's Python based. So I have actually Python written make files. So you see that for SKY130, what I do is I extract the SPICE models from their big, how should I call it, mess of models, and I just combine them in my own models to easily do them. I generate SPICE files. So if I threw a tree, so what he has done, you can see that I follow a little bit this open PDK standard of defining your subdirectories. He has generated an IO lib, a macro library which contains the bipolar transistors, and then the standard cell library. And for each of these libraries, he generates a GDS file, and for the standard cells also the Liberty file, a SPICE version, a Verilog, and a VHDL version. I also generate files for Coriolis, place-out support, but yeah, we can add open road, open lane support later on. Again, open source, start with something and then continuously improve it. And I also generate some DRC and LVS deck for K-layout at the moment. But this is not a one-to-one translation of the IHP. This is based on definition how we define the transistors and devices in this PDKMaster file. So I focus on portability, so I may make some shortcuts so that I make a design rule a little bit bigger than the theory, but then it's easily portable between these different technologies. Because if I now go into the IHP one, do the same thing here, clean. So then you can see that it generates the GDS file for the two. So you see that there is less support here. I only have the GDS files here because the VHDL and Verilog generator uses also the tool from libsys which need a model for their transistors to run. So that's then the first start here of the design. So that was my first demo.
But then there's already this kind of simplified LVS for digital design available.
Yep. But it's pure, it's structural, it's only structural. But I think that was one of the questions. Just a structural LVS, it's not PEX yet. For sure. But that can be added also. Yeah, but it's only the NMOS, the MOS transistors. So, but we can discuss about the bipolars and all the other things, because I probably have to add, if it's not a normal bipolar or another device, I have to add it to PDKMaster support for these devices. But that can be done. Huh? So if we then go to K-layout, you can see here, this is the flip-flop with a active low reset signal, and this is the Sky 130 version of the flip-flop. I played a little bit with the colors coding so that it's the same, and this is the 1.2 version in IHP, and this is the 3.3 version in IHP. So you see that the main difference is that here the L has to be bigger for the 3.3 device, which is normal. But you can see that the structure of this is the same, but that it still takes into account all the spacings. So you can see here that the pin is here and that it probably has shifted to other locations over here. But yeah, I think I can already do some quite complex structures this way. So, yeah? Did you show the code? No, that's this.
But in principle, that means we could then also easily transfer IP generated in Skywater technology to IHP technology and vice versa.
And that's kind of the whole point of PDKMaster, right?
Yeah.
You're abstracting the PDK.
Yeah, so, yeah.
This library, of course.
So actually this is generating. Yeah, so actually this factory is actually the class that generates the standard cells. Yeah. And it uses the code from this flex cell library. but going into detail in this code, I think is going too far for this presentation. But yeah, so the thing is, I have a similar way of describing the technology in all the technologies, and in that way, I can have one code base on top of it that generates the standard cells. And it derives the data needed for generating from them. Of course, each node is a different technology. So I want to give then a last teaser for what I will present in, because yesterday there was a discussion about command line versus GUI. And to me, a Python notebook is a good, this is, for example, a Python notebook that I made for an SRAM cell design. So you can have documentation and your code combined in one flow. And yeah, I'm not going to detail, but you can explain which parameters you define on. But in free silicon conference, I will. But you can easily make a tutorial in this one so that you can get students going. But then they are not locked into this notebook because they can make new notebooks, copy from different notebooks. So in my mind, that's a good way of combining these things. So the status, I did some tape outs in 0.35, 0.18. The main thing is that the layout generation API is not fixed yet. And so I don't want people to use it already for tape outs, because typically if you do tape out, you want to do a tape out a year later. And even my tape outs I did, I will need a lot of work if I want to redo these tape outs because they are not maintained. So if then you have an external compiler, that's maybe conservative I have because I was support guy for the standard cell libraries. So Sky130. So if you want to contact me, you have these email addresses, and I also have a community Gitter on Element. You can also access to Element. Thank you.